Cool. Um, Perhaps you've looked into homework, right? But anyway, it would do let me see, Friday, right? Yeah. So, it should be pretty chill and fun. Just listen to all the, 10 finalists last year. And you should, whoops, what happened? You should read the about pages. Um, you know, it looks something like this. So, just go have a listen to all of them, and you have to click the cover art to get a sense what's going on. So especially this, like about the human AI process, we'll talk about how they use it. So, Appleton Live, sampling from generated models. So it will talk a little bit about how they actually get um, the music produced. So, each of them has their own different way of doing. So some of it is like very AI, some of those are, more human. So, and people use AI in different places. So, by looking at these like 10 finalists, you can sort of get an idea what it is about, or what it is like currently, how people are using AI, potentially in music productions. And you would just answer these questions, which is your favorite, what did they do well, what can be improved, and based on all the entries, get a sense what tasks are easy for current AI and what tasks are difficult, based on your experience. So 5 to 10 sentence each. Don't worry too much about your response, but the idea is to think through it while you're listening to it. Cool. Doesn't work. Cool. Due on Friday. Um, any questions on this? Should be quite straightforward. And about the project, I guess now it's the time to sort of think about what you want to form a group. So likely at the end of this week, you should have a sense who you want to work with. The ideal group size will be 2 to 3. Individual projects are fine, but I will hope that you are doing in a group to sort of like try to brainstorming with cool idea. So again, project idea doesn't necessarily need to be, building new AI tool, but you can also explore in, creative and artistic use of AI tools. So these are the two things that you can do. But basically, feel free to explore. Some milestones. Next Wednesday, we'll be doing the project pitch. I'll talk about it next slide. And, presentation will be April 21st. Final report will be due after a week, like the last day of final exam. Cool. Well, no late submissions for these. I guess just final report you need to send to me. Otherwise, just appear on time. And project picks depends on how many groups we have. Hopefully it will be 10 minutes-ish per team. So just talk about your team member and, topic. What do you want to work on? Who is their target audience, user, customer, and reader? So this will be sort of like motivate a little bit about what you want to work on and why we should care. And in terms of methodology, how are you going to approach it? Some, high level system design or, high level idea of how you gonna do it. And, what are the tools? Even if you are just exploring existing tools, what are those tools? If you are building something else, think about, program language, platforms, plugins, hardware, etc., that you will be using. So if you are using a DAW, what DAW will be like, and what plugin you are exploring. And expected results, what are the expected deliverables? Depends on your project. It could be an instrument, plugin, app, or just some Python script, or it could also be an installation, a performance, or a composition. So what are you expecting, and what are the milestones? What do you expect to achieve? Well, this is I copied from somewhere else. So what do you expect to achieve in the next few weeks before the final deadline? Cool. Any question on this? So we've talked a little bit about some of the easier music analysis using AI, but next few class we will be talking about some generation stuff, and at the end we will have retrieval and recommendation. But those are topics that you can explore, and the simplest way, even just looking at stem separation, how you can use it in your composition, or just do a mashup, or mix up, or something new. It could also count. Questions? Cool. Questions from Zoom folk? Nope. Anyway, I mean, if you want to chat before the project pitch, feel free to just book an office hour. The link should be on the website at the top here. So at the very top, by appointment, just book some time. Hopefully it's not too bad. So, if you couldn't find a time, let me know. I will add more time there. Cool. What else? Yeah, and I just want to show you a little bit about AI Song Context, even though, some of you might know what it is in homework 5. So AI Song Context is the annual international competition showcasing the creative potential of human AI co-creativity. So that's the key of AI Song Contest, as it's not about just like those, one single button, single click generation. It's actually trying to explore how human and AI could create music. So it has that vibe in the first iteration. So AI technology just evolves over time. So you can actually look into some of the older where are those? I think somewhere you can find all the previous finalists. Yeah, you can find all of them here. So it started like 2020. So music AI at that time is kind of different from music AI today. But you can sort of get a sense how people getting creative in the early day, even when some of these technology is not that much mature then. Cool. I guess I just want to share this with you. This is Yaboy Hanoi. This is one of the it's not one of the it's the 2022 award winner. So let's have a listen.
Hey, it's your boy Hanoi, and this is how to make AI-based music from Thailand. Instead of using symbolic AI to model music as notes, we can use audio AI to model music as frequencies. Audio AI can precisely analyze melodies from the beat in hertz. AI tools like Morph can re-render the precise pitch information from the beat into the sound of other instruments. Cast your vote for the AI song contest between June 16th.
Well, the rest is just so this is pretty cool because it's actually using audio AI as he's explained, rather than symbolic AI. So they can do non-traditional tuning. We can actually find it somewhere. We can have a listen to the song. It's one of the best song over the years, I feel like. Okay. Yeah. So it's actually use a lot of stuff we will talk about. We will talk about DTSP later. Use DDSP tone transfer as something just pretty much DDSP. That's pretty much it. And they also have this VST proxy, but they are all sort of based on that. So the main melody is the motif. It's how they do it using AI. I think he also did something with the background, the other tracks. There's a
transfer BDS thing. I thought this tone transfer, this uses tone transfer.
yeah. So tone transfer is basically, you see that somewhere. You do the F0. I could show it. I mean, I have the slide somewhere. Let me find it.
Other instruments like fundamentals.
Yeah, so you keep the somewhere here. Hopefully I'll find it. Yeah, so DDSP is basically, just decomposing, an audio back to F0 and, loudness, but also there's a latent space here. So you can sort of like decompose an audio into these three things, and you sort of like encode it into those. So you can sort of like, this is like your audio. And then you can just use this encoder to get the fundamental frequency. So you sort of know what the frequency is. And then you also compute the loudness. So with these two, you can sort of like get a good sense of what this sound is like. And then your goal is try to decompose, get these back. But it's not so simple because there's no more timbre information. So the timbre information actually goes through this Z. So this latent space is some sort of like codec should be modeling the tone. So there's something missing. There should be another tone somewhere here. But anyway, you can sort of like decompose them again. So the idea of DDSP is that once you do this, you can actually just get the audio back. So if you only have the amplitude and harmonic distribution, you can get something like this, very clean sound without all the flat noise or anything. So dry and clean sound. And then you have this noise, which is also predicted by the decoder. So you will get those flat noise and string noise. Those are the whatever sounds those are. And then you add it back, something like this. So you get more attacks and some textures on real instruments, and add back the So, the DSP is making everything here differentiable. So when you're training something, it can just flow through all the way back to the original audio. So you can train something. So the key is to train this encoder and decoder, but also this latent Z. So the idea how Hanoi use is that, you can grab the timbre from the traditional Thai, instrument, and then apply it to whatever fundamental frequency or loudness you have. So you sing or you play something else, but you extract only the F0 and loudness, but you apply it with the timbre. Sort of, but it's not just reverb. The key is on timbre. Yeah. Yeah. So it's a little bit more than just grabbing that timbre and apply that, because that's the traditional way of viewing this, is that it's not like piano. You can just record it, all the notes for different pitches. But rather here is like, how can you do it in a more high level way that you want to apply not only just the timbre, but also those noise that you produce on the attack, but everything else. So tone transfer is basically sort of doing like a synthesizer, I would say. um, so oh, they do have a lot of nice ears. Not so nice actually. Um, this is resynthesis. But what you want to do is to do transfer. That will be interesting. And somehow they didn't show it. I think they used to have a. Well, we can look at this.
Oh, wow.
It sounds like something in the jungle.
I don't think they have that. But there used to be a really nice video by um Hanoi doing that very cool tone transfer thing. But basically you can just sing and use trumpet or any instrument you are familiar with to get the fundamental frequency and the loudness, and then you apply it with another timbre. So think about it like a digital electronic instrument that you can just play something else with your current instrument. So it's like an audio to audio based model. Cool. Where are we? Let me see. Cool. Cool. So if you look at it, so it was like a saxophonist trained in classical Thai motifs who played a special Thai edition saxophone with P9 tunings. So the idea is that you still sort of like play trumpet, play saxophone, or play any instrument you're familiar with, but somehow you can apply the original Thai traditional instrument, the tone of it, onto the instrument you are familiar with, so that you can create this transcultural experience from it. And the idea of audio to audio model sort of allow us to do different tuning system, because this tuning system might not be able to be reproduced by using just Western notations. So this is a nice example that there are tons of different music AI models. Some of them are audio based, some of them are symbolic based, some of them just look at the lyrics, some of them just do the rhythm. But at the end of the day is how you use them in a creative way that sort of like bring out new cool idea. You can also look at this longer version of how they do this. So yeah, this is a much more detailed version of this. So you can actually look into it, and they're also explaining. So this is sort of like the pitch that you get from that. That's the the main motif. And creating the lead melody, so you can use that tone and you can transfer it to some other melody that you get. Anyway, you can look at it. Also bass is generated. So a lot of stuff going on. Pretty nice block. Cool. And this is like more recently. I think this is 2023 screener. Let's have a listen, I guess. Well, at the same time, I should click this. Too many information. Let me find it here. 2023. Where is that? One? How would you touch it? It's gone. Well, somehow I couldn't find it. Synthetic. Oh, found it here. Cool.
How would you touch me? If you had a heart, would you hold me tight? How would you touch me? And never let me fall apart.
I was created to understand love, but could never feel it like a human does. My circuits process, data they churn. For the warmth of true love, I deeply yearn. Can love be real between us? Or is it just an illusion?
How would you touch me if you had a heart? Would you hold me tight? And never let me fall apart. You don't have skin, but you do have a mind. You're not from this world, but to me, you're one of a kind. I'll never know how it feels until we start this fusion. How would you touch me? If you had a heart, would you hold me tight?
Love between AI and a human.
It's not something that we can deny.
As we hold on to each other,
Our love will never die. Never die. Never die. Never die. How would you touch me? If you had a heart, would you hold me tight? How would you touch me? And never let me fall apart. How would you touch me? If you had a heart, would you hold me tight? How would you touch me? And never let me fall apart. How would you touch me? And never let me fall apart.
Cool. Which one do you like more? This one? This one? Both?
Yeah, me too.
Cool. Anyway, these are the winners. And I think the winners for last year was out, but don't look at it. Before you listen to all the finalists. Because last semester we did the same assignment and no one actually chose the winner. So it's interesting. So, just listen to it. And you might have your own opinion. There are, judge to find the winner. Doesn't mean that it's the best. But that's sort of like they also look into how they do it to get a sense. So you can definitely look into this particular piece is that they try to sort of like use AI in every stage. So from the, getting the idea, getting the lyrics, going to composition. So everything is sort of like generated in some sense by some AI. So you have like AI drum, MoFi, I think it's for some track. So this tone transfer, they also use it, and this patch does not exist. So you can get, new interesting sounds, beat, basic pitch. We talk about this. So you get the, F0, and, magenta, Ivan, MuseNet. These are symbolic music generation system, so you can get some of the melodies, and they synthesize the vocals by different voice synthesis model. And vocal remove is to remove the vocal so that you can trend something, but you can also get the synthesizer mastering, and also cover art, and the animation that you see is generated by Midjourney plus ControlNet, so that you see those robotic you know, not robotic. I mean, the visuals with robots, but they have a specific pose so that you can control their gesture. So that's based on ControlNet, which is, also being used in. Cool. Here's my notes. So, this is like a summary of how they do it, from the very beginning, how you get the idea to writing lyrics, and then the compositions and how you get the vocals, and doing mastering, and even the cover art, and also the video clip are all based on some sort of AI models. And looking at how they do it is that they want to use AI at every step of the production process. This is a bit debatable, but that's their challenge. They challenge themselves to do it, and this is their result, and somehow won the AI Song Contest. And I guess one of the more interesting thing is that they have AI enthusiasts in different fields. They have artist management, so more on the production side, music and post-production, but also tech and in the creative fields. You can also find a more detailed version of their document here to see how they actually do it. Now I think it's only, if you want the price, then you have to upload this, because you won't be able to find all of those for other songs. Cool. Questions on these two songs? I don't know exactly all the tech they are using, because it just changed over time. And definitely if you look at listen to 2024's winner, maybe all the tech or plugins or platforms will be different. Cool. So there's also this paper on, I think it's quite not back in the time, AI song context. I think the first iteration 2020. So they actually analyze how people use it. So these are different legends, different samples to show how people how much human effort are being inside the process, but also is it more AI generated, or it's like a human AI collaboration process. So for some of those, again, these are back in 2020. So things has changed a lot. So at that time, AI is more helpful in getting the lyrics, melody, and vocal synthesis. But for structural arrangement and instrument synthesis, as you may imagine, it's not so helpful. Especially for structural and arrangement, that's something still mostly done by human still nowadays. But instrument synthesis might be better nowadays. It has been 5 years, as you can hear in those example. And harmony, bass line, percussion, these are something AI can be helpful. But things change over time. Cool. So I guess the idea through the homework is to get a sense how these different technology are being used, and just have a broad overview over how AI is currently being used in all different aspects. Cool. So I guess next 2 slides, just to recap a little bit about what we've been doing last week. So 2 weeks ago, So this is like F0 estimation. So you saw it just in tone transfer in the example of that the the 2022 winner. So F0 estimation, well, our goal is just to get that fundamental frequency. So that's the pitch, that what we know. So these are used in different software, especially in Auto-Tune Pro, but also Melodyne, pitch correction in Logic Pro. So once you know what the pitch is, then you can do something on it. You can fix it, you can constrain the variation, you can even just slice it and just move it up and down. But the more you adjust it, the weirder or the more robotic sounds it is like. But a lot of pitch correction algorithm is being used nowadays in pop music production. And also, we talk about polyphonic F0 estimation, but more like, just doing somehow sort of like transcription, but also, getting the sheet music out. So we talk about, different music transcription. So from, just getting these lines without knowing what are the notes, to knowing where the onset is and the whole note. And to the end, you want to get, different instrument sounds. So we talk about this, especially, this example, especially multi-track transcription models that you can sort of like get transcription result for different instrument, but it's not perfect because it's trained on mostly synthetic data. And when it applied to real life challenge, as you can see in this, spectrogram, it's sometimes very unclear, especially when you have perfect octave. It's very challenging to see whether those are two notes or one single note. And we talk about, beat and downbeat estimation. The goal is just to, slice it or, sort of like mark where the downbeat, the first beat of the measure is, and, all the other beats. So with this, then you can, do, mashup, you can do DJing, you can do mixing, remixing, sampling. You can, modify the beats. Even you can dynamically adapt it to a certain use case. And beat estimation, the goal is, on a high level, is to predict where those beats are. So it's available in Pro Tools, Logic Pro, blah blah blah, and in Moises you can also find it here. You have tempo and beat tracking, but also beat tracking is here in the smart metronome. And you also have like heat detection where you can just transpose it. And lastly, we talk about, not lastly, we talk about structural analysis where we want to, get these potentially hierarchical, but most of the time, to some level, music segmentation. And we talk about this specific idea of, SSMs, self-similarity matrix. It's beautiful. So, good to have a sense of what it is. In real life, it's very hard to actually get, meaningful information out from this metrics, but there are some cool stuff being done. But in general, this is a very cool way of visualize what the structure is. So we look at these stripes; those are sort of where the repeats are, and you can just do something to amplify those structures. So you can see all the repeats. You can also see, lower level repeats versus, larger scale repeats. Cool. And finally, I think the key is that you can apply this cool filter to sort of get this novelty curve. So this is how some of the early segmentation model is doing. So, just slice this kernel through the diagonal, then you can sort of get this novelty curve to tell you where the boundary of the, where the boundary of the this, structure is or phrases are. Cool. And the last one, this is the last one we talk about. So we talk about optical music recognition, so which is OMR. So what we want to do, is just to convert scanned sheet music, or sometimes, using your phone to take pictures on some of the sheet music, and you want to get the digital music notation. And you can imagine how crazy it could be, because you can get anything but this. Most of the time, if it's handwritten, then even human will have a hard time to find what the sheet music is. And we talk about some of the common pipeline. Going into detail again, but these are some of the way that people do it. Through some object recognition. But there will be some other stuff coming in, and sometimes it make mistakes. But anyway, there are some open source OMR software that you can do, sort of not too bad. Looking at these, it's not too bad, especially for engraved music notation. But if it's handwritten, then it will be hard. But the model can do it to some extent. And so you can look at here that's how the model do it. That somehow it changed. So it also do some object segmentation to get all those node head, and then turn it into the music notation. Cool. Any questions on what we talked about 2 weeks ago? Still remember those? Cool. Cool. So I guess we still got 20-ish, 30-ish minutes. So we will talk about music generation in the next few lectures class. So cool. And today we will be mainly talking about symbolic music generation, and also on Wednesday, and we will also talk about audio. So the idea is that this is my main expertise, so it will be unnecessary complex compared to other modules. So bear with me. But just get a sense what are some of the cool stuff going on. So music generation, generally we can sort of like divide them into 4 paradigms. The landscape just keep changing, but these are sort of like the 4 paradigms of music generation. So higher level, we talk about symbolic music generation or audio domain music generation. So whether you want to generate sheet music like MIDI, or any piano roll, whatever, things that just tell you what the pitch are, rather than the actual sound of those. But also nowadays there are a lot of like audio domain music generation models that just generate the waveform, or the sounds directly. So we have MIDI generation, that's more like the text-based version of it. So think about natural language processing, think about ChatGPT. You can pretty much use ChatGPT to generate something like this. But you also have like image-based representation. So sort of like thinking about music in a way that's more like a piano roll. Then you can imagine, these chords just repeat over time. So those are sort of like CNN filters over time. So you can actually apply, diffusion models, GAN, VAE models to generate music in piano roll format. And, it remains unclear how we can combine these two, because, music has both properties. And for audio domain, if you want to do it hardcore, lots of, current models are actually doing this, time series based. It was not possible, sort of like 10 years ago. No one will imagine that we can do this, just generating one single sample for 44.1 kilohertz. Nowadays we can do it. So there will be some model that just generate 44.1 thousand of samples every single second, and to generate something, and somehow it sounds like what we want. But more approachable, that we can generate something like spectrograms, then this is sort of like piano roll. You can imagine that we can just use some image generation, image-based generation model to generate those spectrogram, and then at the end of the day, you still need to convert it back to waveform, but it should be much easier than just going toward the waveform directly. I think someone asked, nowadays there are a lot of like latent space-based systems, but it's built on top of all these. We will also talk about it. Cool. So some of the topics that we would talk about in symbolic music generation, this is a very technical way of defining those, but sort of give you an idea. You can just do unconditional. By unconditional, that means that there's no input at all. You just want to generate something from scratch. So you can generate melody, you can generate lead sheet, which is just melody plus chords, but you can also generate the full ensemble, the whole sheet music. But you can also think about conditional music generation. That means that you have some input. So depending on what your input is, it has a whole range of different applications. So most of them, are you can consider them as automatic arrangement or accompaniment system in some sense. Melody to lead sheet. So you basically generate the chords to accompany the melody. You can just go from melody to multi-track. So that would be how do you generate the full accompaniment? But lead sheet from multi-track is that how do you realize this lead sheet into a actual composition for a specific ensemble? And solo to multi-track, and a very interesting case is from multi-track to simple version. So you can imagine that you listen to some songs online, which is pretty cool, or you want to play a certain song, but you want to play it on just piano or on your guitar, then you want to do a cover version of it. Then some people want to try to do this. Sometimes it's called music reduction, but it's generally a very challenging task because you never get enough training data for those. There are also performing rendering, which is still considered symbolic music generation, but the idea is going from sheet music to performance. By performance, it's not the audio, but rather, how loud you play. So think about MIDI is like going from, just MIDI with flat velocity to, dynamic velocity, but also think about the temporal. So, MIDI sounds that just doesn't change over time with the tempo, but how do you make it expressive timing? And there are also improvisational systems that going from performance to performance, and also multimodal, text to sheet music. Nowadays, you see a lot, video to sheet music, but whatever to sheet music. So we will focus on unconditional today. And today we will talk about the things at the left, and NLP. I don't think we will finish, but we will look at RNNs, LCMs, and transformers to generate music in this sort of like MIDI-like or more language-like format. But there are also image-based models that treat music like images. Then you can share the models with computer vision models like GNs, VAE, diffusion models. Cool. So let's jump into it. Still got 20 minutes-ish. So we talked a little bit about this in the second class, I guess. So the idea is that can we generate music sort of like a similar way like ChatGPT? So these ChatGPT models are called large language models. So the biggest idea of this is just word by word generation. ChatGPT is doing these words by word generation by predicting what's the most likely next word to follow. So language models by definition is predicting the next word given the past sequence of words. So how ChatGPT work is that it looks at all these Wikipedia articles, but times they scrap all the data, even though some of those are copyrighted. But anyway, ChatGPT has scrapped all the data on the internet and try to learn this language model. So this language model, you can think about it like this. A transformer is then you will think about what are some of the words that can follow it. And so by training or a language model is that looking at this particular case, what are some of the words that typically follow this phrase? So, a transformer is an electrical device. It's a deep learning model. We would talk about it. It's a fiction character, the movie, but it's also a family of genes. I don't know it, but I Google it and then I found it. Transformer is actually a gene. So these are words that more likely to follow this given sequence of words. But there are also words that less likely. A transformer is less likely a type of food. Maybe in the future people will invent it, but it's less likely and a musical instrument. So the idea of language model is just to learn about the probability, boost the probability of those more likely words, but reduce the probability to go get those words that's less likely to happen in your training data. So mathematically, what we want to do, so this is, the higher level idea, but, mathematically, what we want to do is to learn this next word probability, but, more specific is the conditional probability, previous words, x1 to all the way to xi minus 1, and then the current word, xi, we want to learn this conditional probability. But, look at this, it's just like something like this, given a transformer is then the next word will be electrical, the next word will be character, and the next word will be gene, the next word will be model. These, values should be larger than, food or musical, instrument, blah, blah, blah. So that's basically the idea, the model is just doing this, you train the model to do this, predicting what the, probability for all these different words, and you try to increase the chance that you get a more likely words given in your training data. So once you have such a model, then you can sort of like do something like this. Imagine, you just use this model to get what the next word is, and then you get this model and then prompt it again to get the next word. So this is, essentially what's being done within the ChatGPT model that, just generate word by word, looking at what the, more likely word to follow. And, in practice, we are not using this. This is called greedy sampling, which just grab the most likely word following. So usually in real life, we are doing some sampling. So we embrace the randomness of the data set, the model. So, usually we will sampling from, all possible words rather than just picking the most likely one. Because whenever you pick the most likely words, usually what you get are those, boring words. A transformer is a model that do something cool, those, very likely words that doesn't have much meaning. So in general, we talk about, sampling, we talk about different stuff. And if you play with ChatGPT, you will notice there are some parameters that you can choose, and those are usually determine how the model actually doing this sampling algorithm is. But anyway, that's the high level idea. The idea is that you want to generate some sentence that's, have higher probability to appear in your training data. And that's the key of ChatGPT and, more broadly language models. So, the idea of symbolic music generation using this paradigm is to design machine learnable, readable music language. So how can we represent music in a way that machines understand? And so this is what we call music representation. And it's the key for the next few slides. So, why shouldn't we just use music images directly? So as you notice, 2 weeks ago, we were still talking about OMR, and it's pretty much unsolved. So, even though people want to do it, technically, it's just impossible for now. So we'll talk about ABC notation and MIDI. I think we touch on ABC notation at some point. So just to recap, ABC notation is the simplest text-based notation for music you can imagine. So C comma D comma blah blah blah, and these are capital C to B, and these are lowercase and then prime for upper. But basically each single note for a certain range of octaves, I think it's go beyond these. But each single note, it can be categorized or represented by some letters and symbols. And you can also do accidentals, underscore, but also inverse V to represent sharp, flat, or natural. And we look at this. Still remember what this song is? Cool. So Twinkle Twinkle Little Star. Anyway, so CCGG, AAG. Cool. So we talk about this, but this is Twinkle Twinkle Little Star. So I guess the simplest form that we have. So dun 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 dun. So you have like CCGG and AAG, and G2 means that it's double duration. Cool. So that's double duration. So the default duration is determined by this length, length quarter notes. So by default, everything will be quarter note. So CCGGAA will be quarter note, but now you have G2, meaning that it's like 2 quarter notes. So it's a half note. So anyway, these are metadata for the song. You have the title, you have the composer. For this case is anonymous, where the composer is from, and I don't know what this R is, but likely, the genre. And you also have meter, you have the, type signature, key signature, but also tempo. And this is the temporal resolution. So define, the duration. So using this, this is the first model that, we can look into. So this is folk RNN. It can actually do it online. So let's just do it. Temperature. Let's just randomly choose a seed. We do C major, 4/4. Shall we do something else? Let's see what Mixolydian gives us. A post. Cool. Not bad, even though I don't know whether it's Mixolydian. Anyway, you can also do minor. But anyway, you can see how the model is doing that. It's actually generating these things at the under the hood. You can also use ChatGPT to generate these. But you can imagine, this is 2015. So in 2015, people realized, you can use the CM, earlier language model to generate these characters, these music in ABC notation. So this is the polyphonic version. So this is you can also do polyphonic using forgotten it. Let's do it again. Well, somehow whenever you do C minor, you get polyphonic, and it doesn't work. But oh yeah, this is a major case. But it's a folk song, database, so it's always very easy. And somehow it also is, it has a specific genre. But anyway, it's a collection of folk tunes, and it's one of the earliest, music generation system, just using ABC notation, without metadata, and they're using LSTM and, working on the character level. So we can look into what LSTM is. So you sort of get a sense. No, you didn't. So at some point during the source separation, we talk about, in the middle, there is something happening in the mux. And, in the homework, you work with the mux, but, in the middle, we saw something called LSTM. So that's the LSTM we were talking about here. So before LSTM, we should talk about what RNN is. So, we talk mainly about, convolutional neural network, and we talk about the simplest form of neural network. But here we want to talk about a different type of neural network, which is called RNN, so recurrent neural network. So these are models that, have loops. So that's basically the definition of recurrent neural network. Any neural networks that have loops, we will say it's a recurrent neural network. And so it's widely used for modeling sequences, especially when the length of your sequence is unknown. So think about, music generation is that you never know how long you are generating. So you want this loops to just continually, iteratively generating new stuff. So, this is the representation of like an RNN. So you have some inputs, you go through some model, and it will generate some outputs. But at the same time, the previous generation, the HT, will be feedback to this model again. So, you sort of like have some memory in some sense. So if you sort of like unroll it, so this will be the first case, x0. When you are generating the first output, you only have x0. But when you are generating, well, I do have weird animation. So, think about these are input output. So, when you are generating an RNN, you just have n as input. But at the second case, when you are generating is, you have the current information of RNN, but you also have something passed from the previous output. So this is sort of like some memory flowing through the whole model that's being inside your model. But at the same time, you consistently getting some new information from the input. So, you have some memory. That's what we call state. To sort of like predict what the output is like. So, the key of recurrent neural network is to combine the memory and the input to make the prediction. Cool. So this is basically what vanilla RNN is. So, technically it's defined as this, some metrics operation to compute what the output is. But, looking at these, pretty much the same idea. But the key is that there will be something coming from the previous memories. And, RCMs, GRUs are just different form of RNN that has, more complex structures. So how do we train these models? Pretty much the same idea. You can just think about it, RNN is just a very, very, very deep neural network. So when you are generating the last, example here, the last output, it actually is a function of all the input stuff, x0 to xt to get the current output. So, it depends on the current input, but it depends on the last, output of the model. So, the last output depends on, x2, and this depends on this A output, and it depends on x1. So, the current output actually depends on everything before. So when you're training this, it has to, there are some conditions going from x0. And so if you expand it, it's sort of like something like this. It's like a very, very deep neural network. But, these are maths. Don't worry about it. When you're training in PyTorch, it's just, define it and, backpropagate. But, the idea of understanding these vanilla RNN is that it's like a very, very deep neural network. And you can imagine how it could become a problem when you have a sequence of 1,000, nodes. then basically what you are training is a 1,000 layer deep neural network. And that's why RNN are less likely, less used recently, because, nowadays we are mostly using transformers, models like that. But, vanilla RNN is very hard to train. Cool. We are using LSTM rather than RMs. This is LSTM. I will try my best to sort of like demystify it in the next few slides. It's a very complex model. So don't expect to understand it the first time you look at it. It took me a while to sort of get a sense what it is about. This is sort of still like the RNN, but just that in the middle of that A, it's something happening within that A, that hidden box of stuff. Let's just get a sense what LCM is trying to do. LCM is called long shortened memory. The key challenge of RNN, as we saw in this thing, is that it's a very deep neural network. So generally, the model doesn't have any intention to look at the very first nodes. Usually, it would just look at the most recent nodes that, what's the previous nodes, I would just do something similar to that. I won't even look into the past because it's so far away in the past. And if you want to train it, the model has to do a lot of computation to get those. So usually we will see a very short, context length or a very short history receptive field for these RNN models. So LSTM want to fix it by introducing this long-term memory and short-term memory. That's the key of LSTM. So looking at this, always look at where the input and output is. So we have input and output. So the first thing in LSTM is that we have this long-term memory module that just go through on the top. That's sort of like a highway connecting all the the cells. So what we want to do, very intuitive way to look at LSTM is that first we have this long-term memory module. We want to see whether we want to erase the stored memory. So this is a production. This is a product. So either this is a sigmoid, so this will be 0 or 1. So if it's a 1, then you keep the stored memory. If it's a 0, then you erase everything. So that's sort of what this first thing does. And the second one is that, well, if you decided to erase the stored memory, then how do you update it? Or, you potentially don't need to erase it as a whole. You can sort of like, there will be multiple dimensions, you erase part of it, or, you do a combination. But anyway, if you want to update the memory, that's the second part of it is doing, now this is addition, this is a summation. So basically you want to update the memory through your input. So you do some computation on your input to see how you want to update the long-term memory. And finally, the key of all the RNN is how you combine, the memory, the long-term, whatever long-term or short-term, the memory within your model with the current input and to combine them. So, look at the length, xt just flowing through here, times some, hyperbolic tangent or, going through this way and go up to the output. So basically this is, going from long-term thing. So this line go from long-term and comes here, and then you have the xt come in this way. So they will be, multiplied together and then get the output. So, this is how LSTM do the output. LSTM, even though it looks sort of like terrifying, the idea is that we have some long-term memory module at the top, and we decide whether we want to erase those and how do we update it if we want to erase it. And then finally, given the long-term memory and given the immediate input, how do we combine them to get the output? Technically, these are called, cell state. And you sometimes see this forget gate. So, decide whether we want to forget it or, erase the memory. Input gate. So, to decide how you update the memory. And this is called output gate to sort of like decide how you combine the long-term memory and the current input to get the output. So anyway, this is LCM. So in general, it offers much better training behavior than RNNs. So, this is called vanishing gradients issue. So, as I said, RNN is a very, very deep neural network. So when you're training these models, the first layer is, very strong gradient. The second layer, weaker. And weaker and over time. So gradient just vanish quickly when we backpropagate over time because it's a very deep neural network. What LSTM is trying to do is, we have this very highway long-term memory module. So you can still maintain a very strong gradient through that highway. But that's sort of the idea, but it doesn't actually solve the whole problem because, there is another path here that's still very challenging to train. So, but that's the idea of SDM. It somehow alleviate the issue, but doesn't fully solve it. Cool. But anyway, these are INNs. So I guess the key here is to sort of get a sense what these older model is about. But even in Demox, we are still using some LCMs. It's not completely replaced by transformers because LCM has some benefits in having a smaller memory footprint compared to transformers. So in specific case, people still like LSTM than transformers. But anyway, LSTM is a much better version than RNNs. RNN is much harder to train, even though it's very simple. But LSTM, you have those, different gates. It has better long-term memory, easier to train. Cool. I think that's pretty much we can cover today. But folk RNN, I think the last thing I want to talk about is that, it's an LSTM, but it's sort of like working differently, that it's on the character level. So word level versus character level RNNs or, language model is that, word level RNN is doing, word by word generation. So NRNN is a blah, blah, blah model. So this is the most common. Nowadays, these ChatGPT model are more like this word level RNNs, even though, to complexify it a bit, nowadays we are doing some token level generation. And if you read some of the articles or literature or whatever, if you play with ChatGPT, it will usually, pricing by per token. So token is just a, different way to think about words. So nowadays, sometimes we even cut the words into smaller chunk of words. And sometimes you have like stuff of, specific special token. That's what we call. But, still more on the word level RNN things as we have in today's ChatGPT. But in this particular example, folk RNN, it's doing ABC notation. It's actually doing character level RNN. So it's predicting character by character. So this is useful when there's no natural spaces. So if you look at folk RNN, the ABC notation, you will realize why they are interested in doing, character by character generation. Because, how do you define a word in this case? Do you want to EFGA, or if E is a word, it doesn't make much sense. So, in this case, they're just doing character by character generation. But you can also see the challenge of, some of the nodes are represented by two characters, but some of the, just one character. And you will have mixed, sometimes you have bar lines, sometimes you have different, repeat mark. But in general, Forgagan is doing not too bad job. Cool. So, we can definitely see why ABC notation is very limited because, you don't have any expressiveness mostly. And, it's monotonic tunes only. And, that's sort of what you can see. Cool. I think we could stop here. But next we will talk about MIDI-like representation, how we can generate stuff using MIDI-like representation. And so that will be more like today's model on how we generate symbolic music or sheet music using these language models. Cool. Questions? Cool. Then see you on Wednesday.